All right, welcome to section 3.3 and section 3.4. So section 3.3, we're going to talk today about piecewise defined functions and power functions. So two different types of functions today. So the first one is a piecewise defined function. So literally look at the word piecewise defined. So sometimes a function is defined in pieces for different intervals of the domain. So remember, domain means your possible x values. So here's an example of a piecewise defined function. The postage paid for a first class letter jumps by 21 cents for each ounce after the first ounce, but does not increase until the weight increases by one more ounce. The table gives the postage for letters up to 3.5 ounces. Write a piecewise defined function that models the price of the postage. All right, so this is what we're going to do. So it's a function, so we're going to call it f of x, as we normally do. We'll say that's equal to. So we're going to look at this first line here. So we're going to say it's equal to 49, right? Because y is actually f of x, the same thing. So 49 if, and we just write down that little interval right there, if x is between 0 and 1. All right, we keep going. Then it's going to be 70 cents if x is between 1 and 2. Oops, 1 and 2. There we go. It'll be 91 cents if x is between 2 and 3. And 112 cents if x is between 3 and 3.5 ounces, and then we put a little curly bracket there. Okay, and there we go. That whole thing is a piecewise defined function because what they're telling you is it's 49 cents on this domain, on that set of x values right there. Okay, and then it's 70 cents if your x is on this interval of x values, etc. down the list. All right. Okay. Absolute value, you've seen this before. Absolute value, the two bars around the variable or a number means absolute value. So if absolute value of x equals a and a is greater than 0, so in other words, a is a positive number, right? So if a is positive, then x equals a or x equals negative a. Okay, and that's why you've seen this before. When you solve for an absolute value, you represent both the positive and the negative value. All right, let's see. So there's no solution to absolute value of x equals a if a is less than 0. In other words, a is negative. Absolute value of x equals 0 has the solution of x equals 0. So we can take the absolute value of 0. It just stays 0. Okay. All right. Let's see. So this is how you solve absolute value equations. So first thing we're going to do is we're going to drop the absolute value bars and represent what's on the other side of the equal sign as both a positive and a negative. In other words, we're going to do this. We're going to say x minus 4 equals 16, and then you have to write the word or there, or x minus 4 equals negative 16. This is how we solve these types of problems, absolute value. Drop the absolute value bars, and then represent both the positive and negative of what's on the other side. Okay, and then solve. So x minus 4 equals 16, well, we'll add 4 to both sides. If we add 4 to both sides, we get x equals 20. Or if we add 4 to both sides here and here, now be careful. We have a negative 16 plus 4, that's negative 12. Okay, and there's our answer, x equals 20 or x equals negative 12. Okay, all right, moving on here. Same process again. We're going to drop the absolute value bars and represent both the positive and the negative for this 10. So 3x minus 5 equals 10, or 3x minus 5 equals negative 10. Okay, So first thing we're going to work with this one first. So we'll add 5 to both sides and divide both sides by 3. So x equals 5. Don't forget the or at each step. Same process, we're going to add 5 to both sides. Be careful, negative 10 plus 5 is negative 5. Divide by 3, x equals negative 5 over 3. And there we go, so x is either equal to 5 or negative 5 over 3. All right, make sure you practice those types of questions. All right. Next we have just an intro here to power functions. So power is where the variable has a power on it, an exponent on it. Okay, so let's see. Here's an example. At 17 feet, the wingspan of a prehistoric bony-toothed bird may exceed that of any other bird that existed. The animal weighed about 64 pounds and soared the Chilean skies 5 to 10 million years ago. The wingspan of a bird can be estimated by this model here. Length equals 2.43 times the width, or the wingspan, or I'm sorry, weight, W for weight, to the 0.3326 power. All right, so first thing they say is graph this function. Well, this is just a quick graph. I'm not going to ask you to graph these kind of problems on the test, but if you punch it into a calculator, it's going to look something like that. Okay, that's just a very rough sketch there. Don't worry about that too much. This is the part. Part B is what you want to make sure you know how to do. It says use the function, so they gave us this function here, to compute the wingspan of a mute swan that weighs 40 pounds. So we're going to plug in 40 for W, right? W is weight in pounds. So here we go. So the length is 2.43, use parentheses appropriately, times 40 to the 0.3326 power. Now remember your PEMDAS, right? Parentheses, then exponent. So you're actually going to do this operation first, then multiply that answer by 2.43. Make sure you do that carefully, all right? Or, of course, you could just plug into a calculator, and you should get something like 8.29 feet, right? I rounded that. I think it was 8.288 or something like that. Okay? All right, there we go. Make sure you practice plugging into those. Root functions. So a root function is a function of the form y equals a times x to the 1 over n power, or y equals a times the nth root of x. So what they're really saying here is don't forget that, if you have x to the 1/2 power, that's the same thing as square root of x. Or if you have x to the 1/3 power, that's the same thing as the third root of x, etc. Okay, so those are important. Remember those. There's just the graphs of those two functions up above, or two regular functions, the one I just gave you. You don't have to memorize those, again, just for a visual. All right, next thing is direct variation as the nth power. So a quantity y varies directly as the nth power for n greater than 0. Remember, that means just n is a positive number. If there's a constant k such that y equals k times x to the n power. So you're going to want to remember this little equation here. Whenever you see the phrase varies directly, you're going to use this equation. Okay? Varies directly means use that equation right there. So that's important to know. All right, here we go. Example, production. In the production of an item, the number of units of one raw material required varies as the cube of the number of units of a second raw material that is required. So let's look at that first sentence first. Right here. We're going to use that first sentence and we're going to create the equation. Okay? So it says varies as the cube. So the only difference here is, so that cube means we're going to put a third power on x. Okay? So it says right here, x is going to be the second units of second material, and y is the units of first material. Okay? So we're going to say y. So it says right here, the units of one raw material. varies as the cube of the second, right? So k times x to the third. So the first one varies as the cube of the second one. Do you see how we wrote that? Okay, so make sure you practice these types of equations. So that's the information they give us there, but now they're going to give us some information. We need to figure out that value of k. So it says right here, 500 units of the first and 5 units of the second are required to produce some number of items, right? Okay, so the first is y. So 500 goes in for y. Times k, we don't know that yet. But that goes with 5 units of the second material. So 5 cubed. And we're multiplying in between there. Okay, so we'll kind of clean this up. So 5 cubed is 125 times k. And I just switched the 125 and the k there because in multiplication order does not matter. Next we're going to divide by 125 on both sides. And if you throw that into a calculator, you will see that k equals 4. Okay, so what that means is we have this now direct variation equation relating the first and second units of raw material here as y equals 4 times x cubed. Okay, we just plugged in the k for 4. Well, 4 for k. You know what I mean. Okay. So now we got to actually answer the question. It says how many units of the first raw material are required if 10 units of the second raw material are used. Okay. So in other words, we're going to say y equals 4 times, well, second units of material is 10. That's the x cubed. So plug that into a calculator. You'll get 4,000 units of that first raw material. And that's the answer they're looking for. Okay. All right. Moving on here. All right, then we have inverse variation. Okay, so inverse variation or inversely proportional, whenever you see that statement, you're going to use y equals k divided by x. So remember now, if it says varies directly, then we're going to say that y equals k times x to some power, multiplication. Whereas if it's inversely proportional, it's y over k, y equals k divided by x, or k divided by x to some power. Okay, for inverse variation or varies inversely. Okay, so let's look at an example of that. The illumination L produced by a light varies inversely, so there's your clue, as the square of the distance. Okay, so let's use that first sentence to write an equation. The illumination L varies inversely, which means it's going to be k over the distance, but it says the square of the distance, so d squared. Okay, so we took that first sentence, converted it into an equation. Now they want to know, though, or they're going to tell us if the illumination is 30 feet, if the illumination 30 feet from the light source is 60 candela, what is the illumination 25 feet away? So in other words, we have to find k. We're going to plug in. So 60 candela, that's the L, equals k over 30 feet squared. Okay, so that's 60 equals k over 900. So we're going to multiply both sides by 900, right? Because multiplying both sides by 900 reduces away that 900, and we get k by itself. So here we'll make sure we know where we're going. So k equals 54,000. So 54,000. Okay. All right. So now we're going to finish this one off. So our equation is L equals K. Oh no, sorry, we already found K. Equals 54,000 over distance squared. So now the question says, well, what's that illumination from 25 feet away? So that's 54,000 over 25 squared, okay, which is 54,000 over 625. Punch that into a calculator, you get 86.4 candela. Okay, that's the units that they use for the illumination. There's your answer. Okay. All right, last section of the day, quadratic and power models. So we're going to look at a quadratic model here. So an example, writing the equation of a quadratic function. So a parabola passes through these 3 points. Okay. Write the equation of the quadratic function whose graph is this parabola. In other words, we need to find A, B, and C. Remember, the general form of a parabola is y equals ax squared plus bx plus c. Okay, so knowing that information, think about what we have here. We have an x and a y, an x and a y, x and a y, right? Since we need to find 3 variables, we need 3 equations. So we're going to use these 3 points to create 3 equations. So watch this. First equation. We're going to use this first point 0, 5. So y is 5. We're just plugging in. X is 0. So a times 0 squared plus b times 0 plus c. Okay, so there's an equation. We'll clean these up in just a little bit. Now we're going to use the second set. Let me change colors here. We're going to use the second set of points here, x's and y's, 4, 13. Same thing though, 13 equals a times 4 squared plus b times 4 plus c. And again, with that last point, we're going to say 25 equals a times negative 2 squared plus b times negative 2. And again, notice my proper usage of parentheses when plugging in. That's very important. Okay, so here we go. Let's clean up this first equation up here. Well, if all those x values are 0, well, that's a 0 and that's a 0 when we multiply, right? So we already know c equals 5. So we already found c. Well, that was nice of them, right? Made that pretty easy. So let's work with the green equation now. Well, we know c is 5, right? So let's plug in and simplify all the other numbers here. So we'll get 13 equals, so 4 squared is 16 times a plus 4 times b plus 5. Okay, because we plugged in a 5 for c. Okay, now well, let's keep working with this one. That'll be better. So let's go on here. We're going to subtract 5 from both sides. Okay. So we'll get 8 equals 16a plus 4b. And then what do we notice? We have 8, 16, and 4. All 3 of those are divisible by 4, aren't they? So we're going to divide all 3 terms, because remember, whatever we do to one side of the equal sign, we have to do to everything else on the other side of the equal sign. So we're going to divide by the greatest common factor of 4. And that'll give us 2 equals 4a plus b. Okay? Nice and easy. Now let's work with the blue equation and clean that up. So let's see, we're going to get 25 equals. Now be careful right here. Negative 2 inside parentheses squared. The negative gets squared as well and becomes positive. So that's positive 4a minus 2b plus c. Oops, c is 5 though, right? Okay, we are going to subtract 5 from both sides. So I'm going to scoot down here just to give myself some room. So that's going to be 20 equals 4a minus 2b. we notice we can divide everything by 2, can't we? So we get, let's see, so I'm going to put that over here. We're going to get 10 equals 2a minus b. Okay, so now look, I'm going to use these two equations. I'm going to rewrite them down here. So we've got 2 equals 4a plus b. And the blue equation, 10 equals 2a minus b. Now what do we notice? We notice we can use elimination here, right? They were nice to us. If we add straight down, well, positive b minus b is gone, 0, right? And then 4a plus 2a is 6a, 10 plus 2 is 12. Divide by 6, so a equals 2. There we go. So now we have a, we have c. We can easily find b. Okay, we can use one of our original equations. I'm going to use the green equation. Okay, I'm going to take this green equation. I'm going to plug in 5 for c and 2 for a. So we get 13 equals, so a is 2 times 4 squared plus 4b, we don't know what b is yet, plus 5. Okay, so we're going to use algebra to solve here. So let's see, we'll subtract 5 from both sides, so 8 equals, and I'm going to multiply all this together. So remember PEMDAS. First square the 4, which is 16, then multiply by 2, which is 32. Okay, so 32 plus 4b, we already subtracted off the 5. All right, so we're going to subtract 32. All right, so we're going to subtract 32 from both sides. So we're going to get negative 24 equals 4b. We're going to divide by 4. So b equals negative 6. And there we go. We found a, b, and c. But they said write the equation of this quadratic function. So we've got to write out that final answer. So remember, this general form is y equals ax squared plus bx plus c. Well, now we know a, b, and c. So a, where's a? A is 2 plus, well, actually, right, b is negative 6, so minus 6x, and c is 5. And there you go. There's the quadratic. That carries those 3 points up at the top. Okay. All right. Now this last problem, I'm not going to cover. If we were in class, I'd go over it with you with your calculator, but that's that. Okay. And same thing with that last one. We're not going to do those. Okay. So thank you very much.